be able to, if the probability of S less or equal to K equal to that. Okay, so I'm actually gonna go into the next slide. Now, what I want to talk about in the next slide is, for me, is what we call empirical rule. Okay, how do I know if my data set follow normal distribution? Apart from looking at the histogram, looking at the normal QQ plots, or conducting Shapiro-Wilk test of normality, or Adamson-Darling, or Kolmogorov-Smirnov test, and so on like that, we can also look at the empirical rule. Okay, when data sets follow normal distribution, we expect that 68% of the data set, okay, I'm talking about this one now. So we expect that 68% of the data set will actually fall within one standard deviation, and we expect 95% of the data set we fall within two standard deviation, and we expect 99.7% of the data set to fall within three standard deviation. Okay, now that's what we mean by empirical rule. Okay, when you take a look at what I have now, so this is the mean. The mean is 64.5. The standard deviation is 2.5. And even after standardization, the shape is not going to change. Okay, after standardization, that's still what we're going to have, except that, this has already been standardized to mean zero, standard deviation 1. I told you the other time, the standardization does not change the shape of a distribution. It doesn't change the statistical architecture of the underlying distribution. Okay, it doesn't change that at all. Okay, so take a look at that apply. So do you know that you can actually, I'm giving this out. Give me 1 second. I'm actually gonna give this out as how do we know the within one standard deviation is basically 68%. Okay, if you can show this, mu minus sigma, okay, mu plus sigma, okay, of 1 over square root of 2 pi, okay, of 2 pi sigma squared, okay, exponential raised to power minus half, okay, x minus mu, okay, or sigma, okay, squared, okay, dx, okay, it is equal to 0.68. Okay, so what I'm trying to say, this is going to give you a 0.68. Okay, multiply that by 100, and that is how I know within one standard deviation is going to be 68% of the data set that will fall within. Okay, now within two standard deviation, or what I'm just going to do, okay, is to change. You're going to see now if you can also, prove. If you can also prove that. So this is going to be 2 sigma, okay, plus 2 sigma, okay. When you integrate all of that, okay, the result that you're going to have this time around, okay, is basically going to be 0.95, okay. Now you can attempt that for extra credit. Okay, that was how we got 95% that we talk about. And of course, if I change that now into the 3 sigma, okay, if I actually change to 3 sigma, okay, plus 3 sigma, okay, now don't forget this is the upper bound, lower bound. Of course, what I'm basically going to have, okay, is going to change into 0.997. Okay, I need you to take notes of that. Okay, and this is that. So you can prove that, send it to me for extra credit. Basically gonna have extra credit. Okay, now I think I put a lot of examples for you, okay, that you can actually try. Okay, now you can try all of that. These are examples, using the normal distribution. Okay, you can try all of that. But what I want to go into now is what we call normal approximation to the binomial. Okay, I told you the other time that in you know it was a De Moivre, okay, a mathematician, De Moivre, that developed normal distribution. And of course, he developed that when he used normal distribution as approximation to the binomial distribution, okay. And in 1783, Laplace, applied this normal distribution to measurement error. And in 1809, of course, the Gauss apply this to astronomical data. But let's talk about the way De Moivre actually seen it, because it was the one that developed normal distribution when it was trying to use a normal distribution to the as approximation to binomial. Okay, so you remember the other time, right? We did a binomial distribution, right? Binomial distribution is a discrete random variable. There's a relationship between the binomial and the normal. I told you the other time, relationship can occur between a discrete type distribution and a continuous type. It's just like a state in the west coast of the United States having relationship with a state in the eastern part. Okay, we talk about the eastern part, talking about the New York, the Connecticut, the New Jersey, and so on, having a relationship with a state in the Midwest, like state of Minnesota, state of Wisconsin, Michigan, Iowa, Ohio, and the like. Okay, the same way here, we can actually have a relationship between the binomial and the normal distribution. Let me tell you now. Let me have a recap on what we did on binomial distribution. We actually use binomial distribution to model outcome, that have a two possible, nature. Okay, that is dichotomous. Okay, you get what I mean? We did that before, right? And when the sample size is large in binomial, it may be difficult or may be complicated, computing that may be very, very tedious, even with your calculator. And because of that, we can actually approximate, binomial distribution with normal. Okay, so this is a theorem. If X follow binomial, of course, the parameters in binomial distribution is N and P, right? Okay, then do you know we can apply the idea of a normal distribution to that? Okay, this is what De Moivre actually did, okay, in 1760 something. Okay, now, of course, what we're going to do, the X that follow binomial distribution, do we know the mean? Of course, the mean of a binomial is NP, right? And the standard deviation of binomial is that. Okay, with that, we can actually standardize the binomial random variable to be a standardized, normal random variable. But let me tell you this, that does not really change the that doesn't change the shape of the distribution. And I told you the other time. Okay, now when you do that now, but let me tell you this, we have a condition under which normal approximation can actually be used. I told you the other time, when the sample size is large, binomial will be difficult to do. And when P is it's not extremely close to 0 or 1, but we have a rule. Okay, the rule of thumb is that the product of N and P has to be greater than 5, and the product of that also has to be greater than 5. Okay, the moment this condition hold in the case of binomial, we can actually use normal approximation, as was demonstrated by De Moivre, that discovered normal distribution. Okay, so that is it. So I'm going to kind of walk you through an example now. Okay, suppose that X is a binomial random variable with a parameter N equal to 12 and P equal to 0.4. Okay, find the probability of X equal to 5 using the binomial. Of course, you can do that. We've done that before, because binomial is a discrete, of course, that can be achieved. Okay, then you can also find the probability. But if you take a look at this guy now, The probability of S lie between 4.5 and 5.5, that cannot be done with the binomial. You know why? Because binomial is a discrete random variable. You cannot have something like a 4.5, 5.5. And in this kind of situation now, the normal approximation can be, called to, can actually be called, to come and answer the question. Okay, take a look at all of that. Okay, so that is exactly what I'm trying to say. Because let me tell you this. In binomial, we can do S equal to 5. If I want to split that to use a normal approximation, I'm actually going to create an interval for that. Don't forget, we normally have a continuous random variable in an interval. Like I want to answer a question that has to do with discrete now using normal approximation. If I actually want to do that, I'm actually going to rob Peter to pay Paul. I'm going to subtract 0.5 from 5. That's going to give me 4.5. And I'm actually going to add the 0.5 to 5. That will give me 5.5. Then I'm going to find the probability of S lying between 4.5 and 5.5. I can actually achieve that with the normal approximation. You know what I'm going to do, right? What I'm basically going to do here, I'm going to standardize, right? I'm going to standardize. If I want to standardize, right? I want to answer this question now. Okay, I'm actually going to use a Z, okay, Z1 equal, okay, 4.5, okay, minus what is the mean of a binomial. Don't forget the mean of a binomial is when you multiply 12 by 0.4. Okay, when you multiply 12 by 0.4. Okay, I think that is basically going to be 8 in a way. Okay, so NP, so that is going to be multiplying that guy by 0.4. Okay, then divided by the square roots, okay, of n. What is your p? 0.4. What is 1 minus p? 0.6. Okay. Okay, so don't forget you're going to multiply all of that. With that, you're going to get a Z1. Then you're going to do the same to get a Z2. You remember what we've been doing? You get a Z2, right? So 5.5 minus, okay, this guy, the same way you do here, divided by this guy. Then from there, you can go to the normal table and check. That's super easy. Okay, now you can do something by trying to compare the result when you use binomial itself and when you use a normal approximation. That was why I said compare the answers. Okay, you can actually compare the answer you got here and here. You're going to see they're going to be close. Okay, so this is another question. Suppose that x followed binomial with parameter n equal to 12 and p equal to 0.4, they want to find the probability of S lying between 6 and 8. Of course, that can be done using binomial formula that we did in the discrete type. Okay, here it's going to be considered when S equal to 6, when S equal to 7, when S equal to 8. Okay, and don't forget what you're going to use. You remember the probability of x equal to x in binomial. Okay, so which is basically n combination s. Okay, or p raised to power s, okay, and q, which is 1 minus p raised to power n minus x. Okay, that's what you're going to use if you want to find this guy out, where you're going to find when s equal to 6, when s equal to 7, when s equal to 8. And don't forget, you already know your n and p is 12 and 0 point, is 12 and 0.4. And of course, if you are given a question like this and you want to use a normal approximation to binomial, okay, you're actually going to rob Peter to pay Paul. Oh my God. How are you going to rob Peter to pay Paul? Okay, because if I want to use a continuous knowledge for a discrete situation, okay, I need to, for us, have a convention that we're going to call a continuity correction. So what I'm going to do, I'm actually going to rob, it's like robbing the poor to pay the rich. Okay, I'm going to subtract the 0.5 from 6 and I'm going to add the 0.5 to 8. That's what I have here. Now with this, now I can standardize because I want to use the normal approximation. Say hex. I'm first going to standardize. Okay. When I standardize, going to do 5.5, getting your Z1. You get what I mean, right? Okay. Z1. Okay. 5.5 minus the mean. Okay. N and P, NP. Okay. Minus the mean. Okay. Divided by the standard deviation 12, 0.4 and 0.6. Okay, when you standardize that one, then you're also going to get the same way you got is that of the Z1. You're also going to come here, plug in 8.5. Okay, also get Z2. Okay, in the end, then you can actually write that your probability, oh my God, the probability of the Z now is basically going to lie between Z1, okay, and Z2, okay, the values that you got, okay, then you can now split that, based on what we've been doing before. Z1, the probability of Z, give me 1 second, the probability of Z less than Z1, okay, minus the probability of Z less than Z2. You're going to check all of that from the table there. You're going to get your answer. You can also compare results. Okay, so that is that. And, the continuity correction, the moment you actually want to use the idea of, you know, a continuous distribution for discrete distribution. Don't forget, binomial is discrete, normal is continuous. I'm actually going to use what I call continuity correction of plus or negative is 0.5. Okay, now don't forget about the mean, okay, of binomial and the variance, okay, and you may want to find the probability of x less than s, or you want to find less or equal to x, or you want to find greater than s, or you want to find greater or equal to. They are not the same because we are now bringing discrete idea now. Okay, we got a discrete problem and we basically want to apply continuous idea. Okay, now here we're just trying to tell the world what the continuity correction is going to be. Okay, because when you are going from a discrete to continuous, there's going to be error. Okay, now how the way actually minimize the error committed is why we need what we call the correction that we call the continuity correction. Okay, so if you want to do probability of x less than s, okay, when you are standardizing, you're going to subtract 0.5 from x before you go on. If you want to do probability of x less or equal to x, when you are standardizing, you're going to add a 0.5 to x. And if you want to do the probability of s greater than s, when you are standardizing, you're going to add a 0.5 to that. When you are doing the probability of s greater or equal to, you're going to subtract a 0.5. Please take notes of all of that. The continuity correction is highly needed. Okay. And what if you want to find the probability of s lying between a and b? I told you the other time, when you are dealing with the continuous, all of these are going to be the same. But right now, they are not going to be the same because we're dealing with a normal approximation to binomial. We are actually using the idea of a continuous random variable, applied to discrete random variable. We basically need to have what I call continuity correction. So if I take a look at this, when it is close at both ends, okay, when it is close at both ends, you're basically going to rob Peter to pay Paul. You're going to subtract 0.5 from the lower bound. You're going to add a 0.5 to the upper bound, just like you are robbing the poor to pay the rich. Okay, but what of in a situation where it is actually open at A but close at B? Okay, take a look at that. You're going to add a 0.5 to A and you're going to have a 0.5 to B. But what if it is actually close at A, open at B, subtract the 0.5, okay? But if it is open at both, okay, open at both, okay, you're actually going to add is 0.5 to this one. You're going to subtract the 0.5. I'm actually going to show you something now really quick. Okay. Now, when you take a look at this guy here, okay, what you did is an opposite of this guy here. This is close at both ends. You subtract 0.5 here, you add, but when you come to open at both ends, you add, and you can see it's an opposite. It's an opposite. Okay, and not only that, another thing that I actually, if you take a look at this guy and this guy, okay, open at one hand, okay, you're going to see that when I did 0.5 plus here, adding 0.5 here is subtracting. Please take notes. Okay, so that is as far as the continuity correction is concerned. I think I put some examples here that you can actually work out. This is where I'm actually going to stop. Okay, tomorrow I'm going to continue from the linear combinations of a normal random variable. I hope you enjoy the lecture today. So make sure you stay safe and have a lovely day. Bye for now, everyone.